In this video, we solve problem 2.4.22 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to solve the initial value problem, and we have a differential equation and an initial condition. Now, when I look at this function and this function, they look very similar. They look like they might be partial derivatives of the same function. Maybe one of them is a partial derivative of that function with respect to x, and the other one is that partial derivative of the function with respect to y. So that would make me think that this might be an exact equation. To determine whether that intuition is correct, we identify the first function. You give it a name. I'm calling it m of x and y, and I'll call the second function n of x and y. If the partial derivative of this function with respect to y is equal to the partial derivative of this function with respect to x, then we know that there's a function out there, we'll call it f, such that this left-hand side of this differential equation is the exact differential or the total differential of f. But that would require the partial derivative of this with respect to y to be equal to the partial derivative of this with respect to x. So let's check and see if we've got an exact equation, and then if we do, we'll solve it. So we're going to compute those two partial derivatives, which you can write in subscript notation like that, or you can use Leibniz notation, which is what I will use over here. So if I want the partial of m with respect to y, that's the partial derivative with respect to y of 4y times e to the xy minus this 3 over y. I'm going to bring that y to the first up to the numerator. That would make that a y to the -1. So it'll be a little easier to compute the partial derivative. Then when I look at this and I want to take its partial derivative with respect to y, I see a function of y times a function of y. So that tells me I'm going to have to use the product rule. Now, according to the product rule, the derivative of a product is the derivative of the first function times the second function undifferentiated. You just leave it alone. Plus the derivative of the second function. In this case, it's a partial derivative with respect to y, times the first function, undifferentiated. And then the derivative of -3 times y to the -1, that would be added on at the end. It's just the power, just requires the power rule. So we'll take the -3 times the -1, which is +3. Then we multiply by y to the 1 less power. Okay, now to finish this, all we need to do is compute this derivative, and then maybe simplify if we want to. The derivative of a constant times y with respect to y is just that constant. And the derivative of e to some power, where that power depends on y, is e to that power times the partial derivative of the inside with respect to y, treating x as a constant. So then if that's the case, I'm thinking of this 4x as a constant. This is the partial derivative with respect to y of a constant times y. Well, the partial derivative with respect to y of a constant times y is just the constant, which in this case is 4x. So the partial derivative of m with respect to y is 4 times e to the 4xy plus 4y times 4x is 16xy times the exponential plus this 3y to the -2. So now we want to compute the partial derivative of n with respect to x and see if we get the same result. And I'm hopeful. Now this 3x over y squared might be written as 3x times y to the -2. If we bring that y squared up to the numerator, we just have to change the sign of the exponent. Then when we take the derivative of this product, this is a function of x times a function of x, we'll have to use the product rule. So we'll have the derivative of the first with respect to x, treating y as a constant, is 4, times the second, plus the derivative of the second function with respect to x. The derivative of the second function with respect to x is e to that power, times the partial derivative of the inside with respect to x, treating y as a constant. So this is a constant times x, where the constant is 4y. The derivative of a constant times x is just the constant. If the constant is 4y, we'll have a 4y out front. That's derivative of the second times the first. And then here, I'm taking the derivative of this piece with respect to x, treating y as a constant. So this, again, is a constant times x, where the constant is the 3 times y to the negative 2. So we're going to get 3 times y to the negative 2 there. The question is this the same as this? And it is. The first term is the same there. I've got a 16xy there, and I've got a 4 and a 4 and an x and a y. So that's 16xy times exponential in the middle, and those are the same. So we've got these two partial derivatives that are equal to each other, which means the differential equation is exact. And if the differential equation is exact, that means that the left-hand side is the derivative, or is the total differential of some function f of x and y. Since that is true, we will say so. There is a function out there such that df is equal to m dx plus n dy. But the total differential of f is the same as the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Well, the only way those two are equal, those two expressions are equal, is if these functions are equal. So that means that m must be the partial of f with respect to x, and n must be the partial derivative of f with respect to y. I call this an existence statement. I think it's really important to put that in your argument so that people know why the rest of the method is what it is. That's what it means for this differential equation to be an exact differential equation. It means the left-hand side of the equation is the exact differential of some function f. Okay, so now we know this is true, and we're trying to get f back. In order to get f back, if you have the partial derivative of f with respect to y, you have to take the antiderivative of the partial derivative of f with respect to x, in this case, with respect to x. Or if you have the partial derivative of f with respect to y, and you want to get f back, you would take the partial derivative with respect to y and anti-differentiate with respect to y. Now, both of these operations are going to recover f partially. They're not going to recover f completely, but when we put these two pieces together, we can figure out what f has to be. So the partial derivative of f with respect to x is m, and that was this function right here. So we had a 4y times this exponential, and then we're subtracting 3 over y, and we're anti-differentiating that with respect to x. Well, if we're anti-differentiating with respect to x, it's just like differentiating, except backwards. These are partial antiderivatives, so we're treating y as a constant. So we bring that 4y down, and we ask ourselves, well, what's the antiderivative of e to the 4y or 4xy with respect to x? Well, that's just like e to the constant times x with respect to x. The antiderivative of e to the constant times x power, where our constant is 4y, is e to that power divided by the constant. In this case, the constant is 4y. It's just like if we had an antiderivative of e to the 3x, we'd have e to the 3x divided by 3. We're doing the same thing here. It just happens to be a function of y. And then over here, there are no x's in this, so that's constant with respect to x. The antiderivative of a constant with respect to x is that constant times x, plus a function that is constant with respect to x, but not necessarily with respect to y. So we'll call that g of y. And of course, the 4y is reduced there, and we end up with, e to the 4xy minus 3x over y plus g of y. Okay, great. And then over here, we want to take the partial of f with respect to y and take its antiderivative with respect to y. In this case, that is 4x times the exponential plus 3x over y squared. And we're anti-differentiating with respect to y. So we bring the 4x down, and using the same argument that we did over here, this is a constant times y, where the constant is 4x. the antiderivative of e to a constant times y is e to that constant times y divided by the constant, and the constant in this case is 4x because we're doing a partial antiderivative. And then this, in order to evaluate that antiderivative, I might bring that y up to the numerator. So I've got a y to the -2 here. So we'll bring the 3x, which is a constant, down, and then we add 1 to the exponent, and then divide by the new exponent, and then add something that's constant with respect to y, but not necessarily with respect to x. So I'll call that h of x. So we get f is e to the 4xy minus 3x over y plus h of x. Now f is also e to the 4xy minus 3x over y plus g of y. So the only pieces that don't match here are the g of y and the h of x. Well, if this function of y is equal to that function of x, they must both be equal to the same constant. So that means our function f is the exponential minus 3x over y plus a constant c. And if you check it out, this plus c fits that form. And this plus c also fits that form. So this is our function f of xy. Now remember, whenever you're solving an exact equation, the function is not the solution. Remember, we talked about this. This is not what this particular function looks like. But if this were my function, z equals f of xy, if I let z take on a particular value, so let's just say that z is equal to like constant k, that would correspond to a particular curve where z is equal to that constant. If I take the total differential of both sides, I get df equals 0. So if I want to find the solution to df equals 0, which is m dx plus m dy equals 0, or the partial of f with respect to x dx plus the partial of f with respect to y times dy equals 0. If I want to find the solution to that, the solution actually looks like this. So this is not our solution. The solution is a level curve of some function of two variables. So the solution is this equals a different constant, and I'll let the constant on the right absorb the constant on the left. So the solution is this, e to the 4xy minus 3x over y plus c equals k, where k is just a constant. Now that is a family of solutions, and it's an implicit family of solutions. We want an implicit solution, but we didn't just want a solution to the differential equation. We wanted a solution to the initial value problem. So we need to use this initial condition to find the right value of k so that the total differential of this side is equal to the total differential of that constant, which would give us, the 0 on the right. So we'll use the initial condition to find the value of k. Well, the initial condition is that y of 1 equals 1, and that means that when x is equal to 1, y is equal to 1. So when I substitute x equals 1 and y equals 1 into this equation, this is what I get. X is replaced by 1, y is replaced by 1. And so we end up with an e to the 4th minus 3 is equal to k. So the solution of our initial value problem is a particular solution, which I'll abbreviate by PS, and that is e to the 4xy minus 3x over y is equal to e to the 4th minus 3. And you can write it like that, or you can subtract that e to the 4th from both sides. That's fine. You can multiply everything by y if you wanted to. All of those would be fine, and all of those would be an implicit solution to this differential equation that satisfies this initial condition.